Big history between nothing and everything. This is chapter 1, the universe, the stars, and new chemical elements. These are my summaries. Threshold 1, which is Big Bang cosmology and the origin of the universe. So in traditional origin stories, they were used to poetically and metaphorically explain the origin of the universe. Early cosmology included Ptolemy of Alexandria in the great work or Almageste, the Almagest, who rejected earlier models placing that the Earth was at the center of the universe and that other heavenly bodies orbited around it. Medieval Christians argued that Earth was sinful and imperfect, whilst a realm of perfection orbited around the Earth, and in the upper universe appeared to be flawless and transparent. And that carried the stars, sun, and planets. It was supported by the medieval Roman Catholic Church. Scientific challenges. 16th century, the Protestant Reformation undermined the authority of the Church. Nicholas Copernicus, a Polish-born astronomer, revived the ancient idea that the sun was at the center and the Earth orbited around it. And there was also the problem of retrograde. Retrograde was where planets in their orbits appeared to travel backwards for a brief period of time. Kepler demonstrated that the planets orbited in ellipses, which accounted for why they traveled backwards relative to us. Galileo was the first astronomer to use a telescope and saw sunspots and moons on Jupiter, revealing a flawed universe. This explains how people were changing their perspectives into how they discovered the inner workings of the universe. Isaac Newton discovered gravity, how all objects were pulled to each other, and the strength of gravity increased as the mass of objects increased. Newton's laws of motion allowed for a greater understanding, of the universe, that is, including the law of inertia, how force equals mass times acceleration, and how every action creates an equal and opposite reaction. Mapping the universe. There's a thing called parallax, which is a change in apparent relationship between two fixed objects caused by the movement of the observer. Greeks saw the principle compared with a background of distant stars to that of other bodies to show how quickly those other heavenly bodies were moving around the universe. This took a year as Earth rotates to the exact same position, showing change of movement displacement. Helping to estimate how far away a star was, in the mid-19th century, telescopes had measured instruments which were more precise. Henrietta Leavitt, 1868 to 1921, studied stars with different brightness patterns. This was known as a Cepheid variable after constellation of Cephus, in which first detected the rate of brightness varied dependent on the size, hence able to calculate how big they were, as in how large the stars were. This estimated the true brightness, that is, if observed from close up. Spectroscopy, developed by Joseph von Fraunhofer, 19th century, created spectroscopy, allowing observers to split light from stars into different prisms. This deduced absorption lines, which are dark lines with reduced energy. So it's a principle in chemistry where lines, due to the presence of specific elements, can be shown, and hence you can see what elements the stars are made of. Big Bang cosmology. Edwin Hubble in 1920 discovered the most remotest objects in the universe, which seemed to be redshifting, revealing that the universe was expanding. The larger the redshift was created by the further away an object was, and that meant it was expanding faster. 1927, G. Lemaitre pointed that the universe was expanding, not static, hence had a history, and that it once was smaller than an atom, called the primeval atom. Fred Hoyle coined the term Big Bang maliciously. Large Hadron Collider in Geneva, Switzerland, smashed particles in high speeds to find out what they are made of. This recreated conditions similar to the Big Bang. Okay, so the origin. Now we're into the juicy stuff of Big Bang cosmology. Okay, 13.8 billion years ago, space-time and energy, matter was created. Space was no larger than an atom. It was incredibly hot, and matter and energy were interchangeable. That's thanks to Einstein's equation of E equals mc squared. Okay, expansion cooled the universe rapidly, which differentiated into different types of forces and matter, which was called phase changes. Billionth of a billionth of a billionth of a second, the universe started to inflate. The universe inflated to the size of a galaxy. A formation of the forces, gravity, electromagnetism, strong and weak nuclear forces were created. The first 20 minutes, matter and energy began to form. Hydrogen formed. 25% of protons and neutrons joined together to form helium, and some protons formed lithium nuclei. Matter existed as plasma. Proteins and electrons weren't bounded together, so they were like flowing around like a soup. Or like the sun. Well, before stars. Okay, photons, electrons, and protons entangled, and the universe was crackling with electricity. So 380,000 years have passed after this, after the Big Bang. And there was this important new phase change. The universe cooled to temperatures similar to the surface of the sun, which is considerably much cooler than what it was before. Photons began to lose energy. Subatomic particles cooled, allowing electric charges to bind together, positive and negative, forming atoms that were electrically neutral. Evidence for this. A. Pinzes and R. Wilson in 1964 discovered cosmic background radiation, which they detected this ancient flash of energy mapping 270 degrees, minus 270 degrees. CBR was predicted by Big Bang Theory, hence proving it true. The cosmic background radiation shows the universe 380,000 years after the Big Bang. And no object in the universe appears to be older than 13 billion years, so we can deduce that it's about 13 or 13.8 billion years old. Okay, spectrographs found out about elements in stars found 75% of atomic matter was hydrogen. Hence, when the universe cooled rapidly, the nuclei of atoms formed. It was of a very high temperature and needed to form elements. Problems. So dark matter made up 25% of the universe's mass. We don't know what it is. There's 20 times more mass that can't be detected. 1990s, the universe was expanding at an accelerating rate, and that was attributed to dark energy, which acts as an anti-gravity, pulling things apart and makes up 70% of the universe. The normal matter, as in atomic matter, makes up only 4 to 5% of the universe, with only 1 to 2% making up lithium and uranium. The other part of matter, normal matter, is hydrogen and helium. Threshold 2, the origin of galaxies and stars. 100 million years ago, first stars and galaxies. So gravity, which is the force of attraction, was due to uneven, inconsistent spread of matter in the universe. Einstein showed that E equals mc squared, energy and matter are the same, and that gravity affects energy as well. Nuclear fusion. Gravity pulled matter closer together, more denser, to the point where protons smashed into each other, forming helium and creating a lot of energy. Stars were formed. Plasma environment was created, as in the soup again. A galaxy is object formed by gravitational link between billions of stars, which was stable 200 million years after. Billions of clouds of gases collapsed to form billions of stars and galaxies. And that's how galaxies and stars were born. Investing in everything. This is chapter 1, the universe, the stars, and new chemical elements. Read my summary. Okay, threshold 1, which is Big Bang cosmology and